Thank you everyone for coming out early this morning. My name is Ruth Jansen, and this is Becca Rousseau, so you know who's who. And we spent 7 weeks of our summer at Taylor doing our research with our advisor, Dr. Johnson. Before we get into all that, I'll just give you an overview of our talk. We'll start by giving you some background and definitions and why we studied what we did. Then we'll get into the main part of our study, looking at some different truncations and the implications of those. And then in our conclusion, we'll talk about some further questions and other research that we hope to pursue. So first, some definitions, different spaces that we looked at. First, we have the Hardy space, H2, which is just the space of all analytic functions whose coefficients are square summable. Then we have the polynomial space, Pn. So this is just the space of all n-degree polynomials. Then a composition operator is defined by some analytic function phi. So C phi of f would equal f of phi. And we're particularly interested in phi, which map the unit disk to itself, and then with f that are in that Hardy space H2, which we just defined. Then a truncated composition operator is the projection of the image of C phi onto Pn. So you just take this possibly infinitely long polynomial and cut it down to a finite polynomial. So we'll look at an example to show you what that looks like. So say we have this function phi and f, then the composition operator would produce this Taylor series, which would be infinitely long. So if we looked at P2 C phi, that would stop at the squared term. If we look at P3 C phi, that would stop at the cubed term, and so on and so forth. We can then represent P and C phi by an n+1 by n+1 matrix. And so it would actually be infinitely many matrix representations of this operator, but we're going to look at one specific case. So we'll particularly look at our matrix with respect to the canonical basis. So we'll basically take our operator and apply it to each element of our basis, and that will correspond to the columns of our matrix. So let's give a look at an example to show you what that looks like. So if we take our same function phi, then we apply it to these first basis elements, 1z and z squared, and that would produce this matrix. So you see each column corresponds with an equation, and then each row corresponds with a term. So our first row are our constant terms, the second row are our z terms, third row are z squared terms. This is finite matrix would then actually be the upper left-hand corner of the infinite matrix that would represent the composition operator. So each time we do a truncation, we're truncating the polynomial and also truncating that matrix to a finite matrix. So then in general, if we just look at P2 C phi, where phi is any analytic function with these coefficients, then the matrix representation would have this form just in terms of those coefficients. Okay, so now getting to complex symmetry, which is a specific property that we looked at. So truncated composition operators, to our knowledge, have not been looked at before. Composition operators have, but not yet their truncations. We haven't been able to find any publications on them. So there's a lot of different areas we could go with that. So we looked at other operators, such as Toeplitz operators, and their truncations have shown to have properties of complex symmetry. And so we thought that that would be a good place to start with truncated composition operators. So what does it mean to be complex symmetric? An operator is said to be a complex symmetric operator if there's some orthonormal basis with respect to which T has some symmetric matrix representation which may have complex entries. So that's where the complex symmetric part comes from. And that's slightly different from being self-adjoint. So we'll look at this through an example again. So using our same phi, if we use this crazy orthonormal basis, then we would have this symmetric representation, symmetric matrix representation. And you can see our complex values there, I over 8. Which are not complex conjugates of each other, so this is not self-adjoint, but it is a symmetric matrix. However, it's usually hard to come up with just the right orthonormal basis to create that symmetric matrix representation, so then we utilize this theorem, which was developed by Stefan Garcia, which allows us to simply take our matrix representation and look at its eigenvectors to tell us if that matrix is symmetric, is complex symmetric, which would then tell us if the operator is complex symmetric. So using an example again, so this is our matrix representation. We'll produce these eigenvectors where the V are the eigenvectors of its adjoint. And then these inner products are all 0, so then since those are equal to each other, then P2 C phi is a complex symmetric operator. This is particularly interesting because C phi of this form is not a complex symmetric operator. So this property doesn't carry over between the two. Then when we looked at some other different functions, we had all different 4 possible cases where either the infinite operator was complex symmetric, but the truncation wasn't, and all those different combinations in between. So that kind of was surprising to us. We thought this property would carry over, so then our research had to go in a slightly different direction.
Yeah, so moving on, we decided to look in general just when would this matrix P2C phi be a complex symmetric operator. So as Ruth showed you earlier, for any function phi, it would have this matrix representation. And to clarify, for the purposes of our study, we decided to just look at Taylor series with real coefficients. So when would this matrix be a complex symmetric operator? Well, first, this is what the eigenvectors of that matrix would look like. And then we combine that with the fact that in the strong angle test, we need to normalize them because it requires union eigenvectors. And the result of that was kind of this weird-looking curve, which we decided to not take in all at once, but kind of look at pieces of it that we could understand. So first, we looked at lower triangular truncation. So this is when phi has no constant term, so we just let phi be a1z plus a1z squared, which would have this matrix representation. And it's actually the case that this specific matrix for P2C phi and that kind of function phi is always a complex symmetric operator. That's because the first two eigenvectors of the matrix and its transpose would both be orthogonal to each other, giving us really handy zeros that make it always pass the strong angle test. So knowing that, we wanted to move on and look at that kind of function again and say, so when would Pn and phi always be a complex symmetric operator? So again, we used the strong angle test and we're able to take advantage of some of that orthogonality. So this curve represented all the values of A1 and A2 that would make P3 complex symmetric, which would be infinitely many values, followed by two intersection points here, which basically represented finitely many values that would make the next truncation complex symmetric. And then here we actually found that once we got to P5C phi, there were actually no values that worked that made it always a complex symmetric operator. So essentially, we would not find a function of that form that always works. We also felt that we were kind of losing a degree each time in our solution set, starting with infinitely many values and going down to 0. So we thought that perhaps if we had a finite Taylor series, this is never going to work.
Then we looked at functions with a linear phi, which we thought would be interesting. And we used a strong angle test that showed that there weren't actually any solutions. But this actually showed an interesting pattern in our eigenvectors, which was kind of cool because we didn't expect that, but came along the way. And so if we have phi that are linear, so it's a naught plus a1z, then we use this notation uin is the eigenvector of pnc phi, and vin is the eigenvector of pnc phi adjoint, and which will correspond to the eigenvalue. We are then able to find these explicit formulas to just find those eigenvectors using our I and our n. So we were able to prove this first formula just to find uin, and then we were able to prove the second part of the stepwise function for vin, just what the last eigenvector is. And then this first part of the stepwise function incorporates the scalar bij, which is in terms of I and n. And then that part, we were able to notice this pattern with looking at larger and larger truncations, but we weren't actually able to prove this yet.
Yeah, so overall, some of the questions that we still have are whether or not we can prove and use this, because we can tell a lot about a matrix by its eigenvectors, as well as maybe some similar patterns for different kinds of functions phi, maybe those that aren't just linear. And also still asking that question, maybe what functions phi would make every PNC phi a complex symmetric operator for each value of n, other than the kind of boring function where phi is just equal to a1, a constant, times c. So we want to give a special thanks to the FMUS faculty-mentored undergraduate scholarship program at Taylor University, because they provided the funding and the setting for our research throughout the summer, as well as our advisor Derek Thompson for all of his wisdom and guidance throughout the project. And those are our references.
Are there some questions for our speakers? No. The advisor can wait. No.
I was just wondering about the eigenvalues. Were they always distinct? Were each one of the eigenvalues different?
Yeah.
And you got the number of eigenvalues, which was the size of the matrix.
Because also the strong angle test requires that they're simple eigenvalues, so they actually do have to be distinct. So we kind of had to make sure that that was always true.
Very nice.
Particularly when we were looking at triangular matrices, the eigenvalues are just along the diagonal. And they had the form that they were just a1 to the power of I minus 1.
And if that a1 was not less than 1, it wouldn't map the disk into itself, which you could, I guess, technically still do, but we didn't like.
Other questions?